do we have computer people paired with non-computer people? So every non-computer person has access to at least somebody's laptop in their close proximity? Right? Yes? Okay. We're going to get started then. Okay. For my Windows people, what you're going to do is you're going to type in WSL. Start that subsystem. Right? For all my Mac people and all my Linux people, you don't have to do this. Once you're done with that, then you're going to go to your Applied Topology folder. Mine's on my desktop, so Applied Topology. And then what you're going to do is you're going to do a git pull. Make sure you pull. I changed the file a little bit. So do that function right now. Git pull. Mine's already up to date, but yours won't say that. It'll download some stuff. We all ready? Yeah? Some people are like, no. It's loading. It's booting up. That's okay. Oh yeah, the Wi-Fi is pretty slow. Forgot about that. All right, are we ready? All right. Last step, well, last two steps, activate. You're going to write Applied Topology. And make sure you capitalize it correctly. It's not in mine, but yours is right. For me, I have to conda activate laptop. What? Okay. So you know your function, your environment is ready when it changed names. So yours should say Applied Topology, right? Everyone says that. We're ready? So last but not least, type in Jupyter Notebook. And that opens up Jupyter Notebook. Jupyter Notebook. Let's zoom in. Okay, everyone's in. Once you type that in, you should end up with this page. This is your Applied Topology folder. We're going to lecture number 2. We're finally ready, 10 minutes in. Yeah. All right, what you're going to do right before, you're going to hit that fast forward button, restart and run all the cells. And then you can scroll right back up. No spoilers, none yet. Okay, so we're going to talk about everything you need to know about Applied Topology. So the first one is simplicial complexes. You have just had a workshop entirely about this, so this should be very fast. You already know everything there is, right? So definition for any given number n, and for any set of vertices, 0, v0 through vn, which is a collection of n plus 1, we call them symbols, but usually they're typically vectors. We have an abstract simplicial complex K on that set of vectors, which is a collection of subsets, excluding the empty set, such that 1, given a face of that complex and given a subset of that face, then that subset must also be in the complex K. This is a very important definition. This is the definition of an abstract simplicial complex. And then this is kind of auxiliary. You don't necessarily need this definition, but given any singleton within K, the set of points of K, the singletons must exist within K. So that's just a weird arbitrary definition. Do you necessarily need that? Not really. Okay, so example, given n equals 5, and we have some vertex set v0 through v5, we define some complex K, and we define it this way. This is very long, this is very verbose, but it works pretty well for a variety of reasons. And visually, it looks like this. Does this make sense to everyone? We've all seen this? Awesome. All right, so our first exercise, as a class, together, let K be a simplicial complex on 5 vertices given by this picture. Write down the sets given by K. Can I have a brave volunteer? Oh, come on, someone. Yes, come on down. Yay, we have a volunteer. But you all get to help him out, right? He's not going to do this alone. You're going to help him. I think so. So let's call this complex K. What is our first step? Someone said name the vertices. I like the word enumerate the vertices, but name the vertices too. So he's already naming the vertices. He knows what he's doing. Okay, that's step 1. What's step 2?
Right.
Yeah. So notice he's writing the singletons. The singletons come first. Then the edges. Absolutely. Do we all agree with him so far? So far he's doing a good job? Yeah? Come on, words of encouragement. Yeah. And then one last one. The face. Oh, it doesn't include the empty set. Nope. No empty sets. Perfect. Thank you. Can we give him a round of applause, y'all? He just came up and did a very brave thing. Yes. So let's just count. Let's do some accounting. Let's check that we're actually doing the right thing. We have however many singletons. That's the number of points. There should be 5. However many edges. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. Right? And then one single face, a set of 3. Right? Yay! We did it right. We're going to remember this. So now instantiating that complex. We're going to use SAGE. So X is a simplicial complex, and we're going to define it on 3 points. Now, what am I doing here, right? I did something weird, right? I didn't explicate all of these relationships. No, I only explicated some of them, right? So for instance, if I only want to explicate, say, a triangle of 0, 1, 2, what do I have to do? Do I have to say all of this? No. There's already the implicit assumption that I have everything below the singletons, right? So I don't have to say it. I can say what are called the maximal clicks, which are the maximal relationships. So I can say 0, 1, 0, 2, and 1, 2. And I can run it. So let's go ahead and run that. 0, 1, 1, 2, 0, 2. And I get this figure. We're drawing simplicial complexes. Great. So now what if I wanted to explicate the triangle with a face? How would I change it? Let's go ahead and do that. All I have to do is explicate the maximal clicks. So I can just change it to 0, 1, 2. Do we all agree on that? If we run it, what do we get? It's filled in. We love it. Sage does our coloring for us. All right, let's keep going. A set, sigma, of cardinality d plus 1 is called a d-dimensional simplex. And the dimension of a simplicial complex K is the maximum of the dimensions of all its simplices. Question? We're not defining, this is just for any simplicial complex. Yes. So, continuing on, we have a face vector, F, of K, which is the set CK of all the faces in their dimensions, where Fi is the number of simplices of dimension I. So I can get for any simplicial complex, I can get its space vector. So this is the simplicial complex with a all its edges as well as its space. So I should get what? 3, 3, 1, right? 3, 3, 1. Make sense to everyone? Great. Now we're topologists. We have some wonderful operations on our topologies, right? You might be tempted to take the product, so the product topology. So let me go ahead and change my x. I'm going to change it back to 0, 1, 1, 2, and 0, 2, which is equivalent to S1. I'm going to rerun that. So now what I'm going to do is I'm going to take the product. Does anyone know what the product of S1 cross S1 is? It's the torus, right? Does this look like a torus to you? No? It doesn't look like a torus. This is the problem when it comes to visualizations, right? They often struggle to get the right configuration to give you a torus, right? This is also the torus on exactly nine vertices, so you're not going to get that beautiful hole in the middle because it's just too compact, right? That you just won't ever find it. You'll have to expand the tessellation. So we can get its 9 vector, that's the 9 vertices, with 27 edges and 18 faces. We can also take the cone, right? We can take the cone of S1, which is homotopically equivalent to what? A point. And it looks something like this. Again, it doesn't look exactly representative. It's close, not the best. And then we can get its face vector as well. Okay, so that example that we just did with our brave volunteer, you are all going to code that. So let's go ahead and grab that simplicial complex. And I want you all to code it. And then what I want you to do is I want you to visualize it. So let's go ahead and code that up. On your computers, go ahead, do it. And the good news is the answer is right here. Now remember, you only have to explicate the maximal clicks. Yes. You can't rotate these figures now. You will later on in the lecture. Questions? No? Why are you two not working together? You're not working together? Yes. PLT. Not defined. Taking its time. But as soon as that runs, you should be able to do it.
Because I think about this topology.
Oh, is it? It might be, you also don't have it activated. Let's see. Desktop. Change directory, applied topology. Oh, you don't have it. Maybe you don't have it installed. Oh, there you do. Jupyter.
No. Thanks. Thanks.
Yep.
Yes.
All right, do we have an answer? Raise your hand if you got the answer. We got some people. Okay, someone who raised their hand, tell me what the answer is. Zero, 1, 2. 1, 3. 3, 2. 2, 4. Let's go ahead and run it. Okay, does this look the same as this? Yes? Do these two things look homotopically equivalent? Yeah? Question. Is it? No, you don't always get the same drawing. It's randomly configured. Other questions? All right, let's keep going. So we have this idea of cellular homology. I'm giving a very basic definition. If someone comes at me for, say, not using the correct coefficients, you can do the math yourself. So definition, define the boundary operator on the set of vertices. We already saw, Paul already spoke about that, but the idea is you want to define a boundary operator. So for example, here on this simplicial complex, we can define a boundary operator like so. So let's define the boundary operator. I like to write it this way. Not everyone does. I like to define it as the two-dimensional vertices to the one-dimensional vertices. So I'll write it that way. And we write it as we only have one two-dimensional vertice. I know you can't see it up here, but I'm writing V0, V1, and V2. And I'm writing it to all the one-dimensional vertices, which is V0, V1, V1, V2, V0, V2, V1, V3, V2, V3, and V2, V4. And what do? All I'm going to say is I'm going to put a 1 for every edge that connects. Make sense? Let's do that again for the second boundary operator. Partial 1, 2, 0. And all I'm writing are all the edges. So V0, V1, V1, V2, V0, V2, V1, V3. Oh, thank you for that. V2, V3, and V2, V4. And I'm going to map them all to their individual vertices, V0, V1, V2, V3, V4. I'm not going to worry about orientation. Technically, you should, but at the moment, you don't really have to, especially if you're working over the coefficients of a CIMAT 2. So, V0, V1, V1, V2, V0, V2, V1, V3, V2, V3, V2, V4. Right? Looks something like this. The rest of them are zeros. The special thing about these two matrices is they're intricately linked, right? What happens when I multiply one by the other? So if I multiply partial 1, 0 by, let's see, I think it's this way, partial 2 to 1. If I compose these, what happens? They end up being 0, perfectly compatible. That's what we like about them. All right, so we have some definitions. We can define the I-cellular homology as the homology group as the vector space F raised to the null space of the first boundary operator followed by the rank, or subtracting the rank of the following boundary operator. So the null space of this, or null space of this minus the rank of this. Do we know what that is already for this complex? It's going to be the H1s, right? What is the H1? 1. Yeah, that's what it should be. All right. Now we define the F, or the coefficient Betti numbers, which is the Betti numbers over a complex K over a coefficient F is equal to the dimension of that homological group, which is equal to the null space of partial I minus the rank partial I plus 1. So let's just look at some examples. We got for a line, which is homotopically equivalent to a point, it should have Betti 0 of 1, Betti 1 of 0, Betti 2 of 0. Triangle, which is equivalent to the sphere, or sorry, the circle, S1. So it should have Betti naught of 1, Betti 1 of 1, and Betti 2 of 0. If we close that up, suddenly it's homotopically equivalent to a point again. So we have Betti naught of 1, Betti 1 of 0, and Betti 2 of 0. And then last but not least, let's have an unfilled tetrahedron. So if you imagine this tetrahedron close to the space, this is homotopically equivalent to a sphere. and I get Betty naught of 1, Betty 1 of 0, and then Betty 2 of 1. Does this make sense to everyone? This at this point, you're like, Greg, this is boring. We already know all this. But one last definition, I hope. So, given a simplicial complex K and the face vector Fik, we denote the ith simplices of K, then the Euler characteristic is defined by an alternating sum. So it can define it two different ways. Technically, you should prove one of the ways, but it's defined as the alternating sum of the face vectors. It's also defined as the alternating sum of the Betty numbers. So we already defined an X up here. Let's go ahead and take a look. Let's take a look at its homology groups. So let's take a look at the 1 over the coefficients of size 2. We get a zeroth vector space of 1, which means one connected component. We get a hole in the middle, which is a homology group of vector size of dimension 1. And then last but not least, we get 0 for our H2s. Is that correct for this? Yeah? We're all in agreement? But now comes the problem. Because this doesn't always work for orientable surfaces, so sometimes we have to extend our language to higher coefficients. This is usually where a lot of people in TDA don't ever touch higher coefficients, right? Y'all are like, coefficients beyond 2, Greg? What? But it's important. So let's go ahead and look at coefficients over 3. Notice the coefficients over 3 are the same, and this is because when you have an orientable surface, it tends to be consistent throughout all the coefficients. So this is coefficients over Z3. Last but not least, we can do coefficients over Z17. Again, the same thing, it's stable. It's an orientable surface. Now we can actually calculate it over Z. And we know what the definition of the Betty numbers is. It should be exactly the dimension of the homology groups. 1, 1, 0. So SAGE is doing all of the work for us. What's the Euler characteristic? It should be 0. So now let's take a look at the product. X product X, which was homotopically equivalent to what again? S1 cross S1 is homotopically equivalent to what? To the torus. And look, do we get exactly those Betty numbers that we would expect? Yes. Let's take a look at the cone. The cone on the sphere, or on the circle, we get exactly the Betty numbers you would expect. So now, actually we already did this. Calculate F2, F3, and the Z coefficients over the complex you already created. We already did that because they never changed it. All right. So you've already learned about some of these figures. This is a review of some of these typical homological figures that we were looking for. So for instance, you have the torus. I have a little animation that shows the torus slowly being deformed into a coffee mug, right? We've all seen this before. So what's nice about SAGE is it gives us access to some of these Platonic figures. So for instance, I can define the simplicial complex over the torus. By the way, this simplicial complex will be exactly the same faces. So if I grab that F vector, it should be, it's actually 2 less. It should be the same. I did think it was going to be the same face vector or the same tessellation. I guess it's a smaller tessellation, but that's fine. So we can get its homology groups. So 1, 2, 1 for all coefficients. Make sense? So when we're doing TDA, what are we really doing? We're playing detective. We're trying to find these Betty numbers. These Betty numbers are like the fingerprints of our surfaces, and we're trying to play detective. So let's go to the next one, the next possible culprit. Here we have the real projected plane. You probably never saw this picture before. Maybe you have. Raise your hands. Did you see this picture before? Yeah? I know you saw it during one of Powell's presentations, because that's how I recognized that it was the projected plane, because this is the R4 embedding of the projected plane. So RP2, we're gonna reference that construction within SAGE. You don't have to. You can construct it yourself using the sphere. And we can get its homological classes. Look. Over the coefficients of 2, I get 1, 1, 1. But over the coefficients of 3, I get 1, 0, 0. So 1, that suggests it's a non-orientable surface. But notice now I have to resort to higher coefficients in order to detect this surface. So you can't just do everything in one set of coefficients. This is what the universal coefficient theorem says. You have to be able to resort to other coefficients. But they are expressive and they are the same across all homotopic groups. Make sense? Yeah? So we know that. We know what the Betty numbers for RP2 is. Let's keep going. The sphere. Notice the coefficients over Z2, I get 1, 0, 1. Over Z3, I also get 1, 0, 1. Make sense? This is exactly what we would expect. And then taking a look at the Klein bottle, I get over Z2, 1, 2, 1. Huh. That's exactly the same as what figure? Someone say it. The torus, right? Well, that's confusing. So imagine you're working over a data set and you get 1, 2, 1 as your Betty numbers. Can you say it's the torus? No, you can't. You have to resort to higher coefficients. Let's take a look at Z3. I get 1, 1, 0. I get different coefficients. Exactly right. That's what we want. That's the goal, right? You can't just use one set of coefficients. You have to try multiples. Can I use Z4? Who says yes? Who says no? One person said no. Who says yes? Raise your hands. Can I use coefficients over Z4? I'm hearing no's, but someone said yes. Who said yes? Because it's not a field. Right? Coefficients have to be a field. Or at least, they don't technically have to be a field. For example, you have a principal ideal domain Z. It's not enough to be an abelian group. Question. It can't just be a ring. It can be a principal ideal domain. So I can use Z4. Yeah, I don't think you can't use Z4. It wouldn't work. Make sense? Has to be prime. That was a trick question. Yes.
The articles that we are in the projects that we are making, obviously Python to analyze the data.
Yep.
But these algorithms implemented in Python, they compute the precision homology with C2.
So or C5, yeah, you can. Yep.
Command or something?
Yeah, it's exactly, yeah. I'll show you. We'll get to it. We will get to it. In Goody, you can do that. You can do it up to like, it's like a prime number in like 100,000, something like that. No, 50,000, like 52,000 something. Anyway. All right, so question, why do we care about homology? So suppose K is homotopically equivalent to L, then the Betty numbers are going to be the same for all dimensions I. So our 0th dimensional Betty numbers, or 1-dimensional Betty numbers, or 2-dimensional Betty numbers, they're all going to be the same. So this is a wonderful way of detecting our surfaces. So next is we're introducing, I'm good on time, we're introducing persistent homology. Now often people introduce it using Viator's rips. I hate Viator's rips. If you came to the Geotopa conference, I kind of insulted people by saying that Viator's rips is not great. So sorry about that. I mean, I'm not wrong, but I want the colors. All right, so let's take a look at this simplicial complex. Notice this looks a lot like Morse theory, right? I did actually grab this from a book on discrete Morse theory. It's a great book. So a filtration of a simplicial complex, I define it a little differently than other books. Some books like to define it as a sequence of nested complexes. I don't like that definition. I like to say a filtration of a simplicial complex is a function from all the simplices on that complex K into R greater than or equal to 0, such that I follow a very simple rule, and that rule is intricately based and tied to the fact that every simplicial complex face must contain all of its subfaces. So likewise, that filtration says for all faces and their subfaces, the subfaces must precede the face. And that's exactly what's stipulated. Yeah, question? No, it doesn't give you a good enough construction. So you can like basically like they're both equivalent. So you can prove one from the other. But if you use this definition, proving the subsequence is super easy because it's a function from R. Like you can basically take the inverse images of R into finite complexes. And so if they're finite, you automatically get the subsets. So you get that for free. Whereas like proving that if you have a chain of subcomplexes to prove that it has a function, that kind of gets gross, right? You have to define equivalence classes on that and just get not fun. So like I said, this is equivalent to defining the simplicial complex with weights assigned to each simplex. So here is an example of a filtration. So we're going to switch to Goody. You already saw something like this with Paul. The way it works is you're going to define a simplex tree, which is the data structure. You don't have to think of it like a simplex tree. I know that word is kind of scary if you've never seen it before. So you can just think of it as a complex. Simplex tree is just a complex. And then you define each of the individual simplices, and you can define with each of the simplices its filtration value. So I go from here to here. Does that make sense? Here's the 0th. I define the 0 with the 0 filtration. Make sense to everyone? Here, for example, is the 11th face. I define it with 11. Does that make sense? Very straightforward. We all understand this? All right, so now we enumerate the critical values of this filtration function as C1 through CQ. These critical values are ordered pairs, and they are often written as C1 equals B1, D1, C2 is written B2, D2, so on, up until you get to a certain critical point, and then suddenly all these critical points are Bj all the way to infinity. These are called your persistence pairs. These are exactly what you will see on a persistence diagram. But they are just critical values of something that's almost of Morse function. Almost. So then, what can I do with that? Well, I just define my filtration. I can get its persistence. Goody lets me do that for free. And I can specify exactly what the coefficients of the homology field is. I'm going to use the 2 coefficients, or Z2. So I'm going to run that. And I get my persistence pairs. Does that make sense, everyone? Yeah? So now let's take a look at 2 things. We have multiple representations for these persistence pairs. We can write them as a timeline, right? I can start at 0th time, and it can continue on. So let's say I'm at time 0. How many connected components do I have? I have exactly 1 connected component. I'm at time 1 now. I have exactly 1 connected component. Time 2, I have 2 connected components. Another component is birth. And I keep going. So let's write that out. Let's draw it. Let's see if that makes sense. Does that make sense visually with what we're thinking? So let's take a look at this diagram. We birth at 0. 1 connected component. We birth at 1, but we connect at 1. Still 1 connected component. Let's do another. 2, completely disconnected. It's an entirely separate component. Let's do 3. 3 is birth, but with an edge. So still 2 connected components. That still agrees exactly with the barcode that we just had. Because that's just the way this filtration was defined. You don't have to. The filtration is an assumption. You've assumed some function on our simplicial complex. Other questions? All right, let's keep going. 4, 4. 5, 5. I still have 1 connected component, or 2 connected components, and that's it. But notice what happens at 6. 6, I'm connecting these two. Does that agree with my diagram? Yes. I connect these two. So fundamentally, what's happening now? I connect these two components. Couldn't I have just made the second barcode keep going versus the first barcode? Couldn't I just have this barcode continue on versus this one? Why not? Someone said yes. Who says yes? Who says no? You have to raise your hand. Can't I have that second barcode be the infinitely persistent thing versus the first barcode? Who says it has to be the first one? Who says it has to be the second one? First one? Second one. Not everyone is raising their hand, so we're going to keep going. First one. Second one. First one. Second one. Some people are raising their hands for both now. That doesn't count. All right. It has to be the first one because it was born first. Is that a little patriarchal? Probably. But the reason is it's called the Elder Rule. You probably read this in Edelbruner's book, The Elder Rule. And it says that if the feature was birthed first, even if two of them collide homologically, you maintain and persist the first feature. So that's why you end up with that. So that's why it's well-defined. Otherwise, if you don't have this rule, you don't end up with well-defined critical points. This is the only way that you can maintain well-defined critical points. So let's keep going in our filtration. All right, we've connected 6. 7. Have I changed it homologically? No? So we keep going. Let's see, 8. Have I changed it homologically? No, nothing interesting. Okay, 9. Uh-oh, what have I done? I've introduced a hole. And notice that gets introduced in the diagram. Let's do 10. I've introduced another hole. 11. Have I changed it homologically? No. And then 12. I've changed it now. I've gotten rid of something. So let's take a look. I had a hole born at 9, and then it died. I had a whole bird at 10, and it died. Or it continues infinitely. That was this one. That was 10. Or this was 10. Does that make sense to everyone? That is how you read this diagram. Now, sometimes it's quite annoying to look at a barcode with many bars, so often this is translated into an equivalent representation called a persistence diagram. They mean the same thing. Since they're ordered pairs, what do we do with ordered pairs? We put them in the XY plane, and we just plot them by birth and death. Further, we know all the deaths have to come after the births, so naturally, they all are above the identity line. And so we draw it like this. They mean the same thing. They're identical representations. So another exercise. Calculate the persistence barcode of the following diagram. I recommend copying and pasting all this code and putting it here. So do it now. You got 2 minutes. Herding cat. Tim, are there any questions in the chat? Nope. Okay. You, did I hear my name? No? Okay. Yeah, one more minute. One more minute. Yes. I always put it 0, 7, so it goes the first the least index first and then the second. Okay. Not all programs need that, but some do. Like I think Goody might. I don't remember. All right. 5, 4, 3, 2, 1. All right. Does anyone have an answer? Raise your hands. Yeah. Okay. One more minute. One more minute. What? Yeah. You got this many seconds left. Hmm? What? You have to get the persistence barcode. Yes. What is the what? Well, we're going to talk about it. What did you get? Did you get an answer? No, it shouldn't be true. It should be a barcode. You should get a barcode. Okay, who has an answer? Do you have an answer?
Which will be the filtration value for 3?
For 3?
Because we don't have a. Well, if I mean, I am a little confused.
You just introduced, so 1 connects to 2. So it's 1, 2, filtration equals 3.
Oh, I see.
All right, maybe we should do this one together. Okay, everyone up here. So I'm hearing a lot of side conversations that they're a little confused. So let's talk about it. Okay. Oh, you got an answer? Okay. So first you copied the simplex tree, you copied all of its filtrations, and then you copied this code here. And you got all of the persistence. Great. Great. Okay, so the people who have it, tell me, what was the H naught? What are the H naught values? 0 to infinity. 1 to 6, 2 to 3, 2 to 3, 4 to 5, 7 to 10, 8 and 9. Oh, yeah. So it looks something like that. Does that agree with our diagram? Well, let's just look at the very end, since it's really hard to check what it is intermittently. But if we take a look at its infinitely persistent features, it should have exactly one connected component. That's one connected component. Okay, that kind of makes sense. That's a good way of error checking if we did something wrong. All right, what about the H1s? 11 to infinity, 12 to infinity, 13 to 14 exactly. Does it persist infinitely or no? No. Okay. So let's take a look. At the very end, how many features persist infinitely? I should have exactly 2, and that's exactly what I end up with. And notice that 14, that ends a cycle, right? So that does agree with what we would think. Does that make sense to everyone? Okay, we know how to code. Vaguely. Okay. Viatorus Rips. So given a radius r, the Viatorus Rips complex over a set P is defined as the complex K such that for given simplexes in K, provided that all of the norms are less than that radius r. I don't like that definition. I gave a definition in terms of filtration. So how do we define that in terms of filtrations? I define the filtration F on sigma to be the maximum radius of the pairwise norms. Does that make sense? Visually, it looks like this. And it looks beautiful. Computationally, it's a monster. It's awful. We don't like it. So visually, this looks like the ball's expanding upon each point. So now let's do Viatorus Rips on the sphere. So I take 100 points. I have some parameterized sphere, and I can plot it. And these kind of look like a point, kind of look like a sphere. And I can get all those points, and I can extract its simplicial complex. It runs pretty quickly. I then get its simplex tree, and I get its persistence, and I get all its values. But what's happening here? Look, I have all of these H1s, all of these Betty 1s. It's a sphere. I shouldn't have any Betty 1s. And I should have a Betty 2, and I'm not getting that. So what's happening? Well, what's happening is I'm not defining an R value that's able to encapsulate the entire sphere. This is one of the fundamental issues with Viatorus Rips. You have to define a radius and then hope like hell that you capture all the homological features until you reach that radius, and you have to hope that you don't break your computer while calculating up to that radius. Viatorus Rips is not good. So this is an example. So what I want you to do is an exercise. Adjust the hyperparameters listed in order to get the correct Betty number. So I want you to adjust these parameters, n, which is the sampling, and r, which is the radius. I want you to adjust those features. Try and get the correct homological features. Do that. You have 2 minutes. All you have to do is change those features and run. 2 minutes. I'm curious.
Yes, doing this. I only try with a list with a
0.7, you're making it smaller. You might want to sample more.
yeah.
Yeah. No, sample, like increase the sampling rate to like 1,000 or 500. It's Viatorus Rips.
Okay.
All right, and then run it. Run all the way down. Run, keep running. And check out the ball. Let's take a look. Notice there's significantly more points, so the radius doesn't have to be as big. Keep scrolling down. Run Viatorus Rips. I rewrote it so I could actually see how long it takes. Because Ripster doesn't tell you, and you're like, I don't know how long this is going to run.
It's not a good tool to compute the persistence.
And then get the persistence.
The persistence variable.
Yep.
Oops.
And then keep going so you can see. Let's check. Let's check what's going on under the hood.
Oops.
No, keep going. Let's see visually. What's happening.
Okay.
See? You have to increase that radius. All right, so some of you are already starting to notice that you need to keep that radius a bit big, right? So for example, if I have the radius too small and then say increase the number of features, so my sampling did go up, but I still have a very sparse ball. So I need more points. All right. One more minute. Did anyone get the right homological features? What?
It was the radius of the sphere, but not the sphere is always the radius is always one.
Correct.
Yeah. I was thinking about the spheres.
No worries. If anything, that's the inverse problem. All right, we're almost done. Anyone get the right homological features yet? All right, let's take a look. I'm getting closer, but I'm still far away. Well, you didn't get the right features yet. It's the sphere, right? Those Betty numbers. You're detective, right? You're trying to get the exact Betty numbers.
Yeah, but what we are struggling with is the visualization that you had before, the one that looked like a spider.
Yeah.
Spider website.
I need more time.
Yep.
Yes.
How many points did you put?
A million.
You put a million? No, you didn't. You put maybe 10,000.
Yeah.
20. Yeah, 10,000. All right, so you're starting to realize that as you increase the number of points, then the time it takes to calculate grows exponentially. It grows a lot. This is, again, one of the headaches of via torus rips. So you might want to keep the number of points small. We're almost out of time, but I wanted to emphasize the fact that for something as simple in 3 dimensions as a sphere, the torus rips is struggling. Why is that? So you can try it again with the torus. And notice again, with the torus, even though I specify a radius of some kind R, I'm still not getting the right homological features. And that's because if I try to interconnect this too much, I'm going to explode the number of complexes. The number of So instead, for your homework until the next session, so you can work through lunch. You don't have to. But adjust the hyperparameters. See if you can try to get it. I'm going to tell you now, you can't. The torus strips on the sphere you can. Keep playing with those, and you will get it. Keep the number of simplices small, around say like 200, and increase ours. But for the torus, you won't do it. Trust me, I've tried. So the drawbacks of via torus rips, it doesn't make use of the features beyond the one skeleton, which is the distance feature. So that's very bad because there's so many beautiful features that can be extracted in higher dimensions. And computationally, it's inefficient as the number of vertices grow. There's no clearly defined maximum radius either. You don't know when to stop. And then certain homological features are not even guaranteed to persist infinitely. So what's the positive of this? Why do we care? Well, it's so bad that there's many veins of research, right? There's some to improve the computational efficiency via torus rips, but there's also some to build more interesting filtrations, which is what I do, and it's what you will do in the next session. So that's the end. Now you get to move on to the final module. You can clap now.